Bode plots today. These notes, they look different, but they're the same. Like, we'll go through, we'll fill in the blank spots, and we'll go from there. So, yeah. Homework due Wednesday. No, there's no pushing it back this week. I had these moments over the weekend. I was like, I let them get away with one. I let them get away with one this week. Shouldn't have done that. Yeah. What?
Your evaluations will be really great.
Oh, well, thank you. In which case, you know what? You're right. It was a good call. It was a good call. Yeah. So last week I mentioned that that problem that we stopped. We said, okay, we found the frequency response function, that vibration example. And I told you we would pick it up again once we've covered a little bit more material, and this is the material on Bode plots. So it's essentially, yeah, question.
Are these notes online?
They are. I sent them out last night.
1 a.m.
Yeah. I sent them out very early this morning. It may or may not have taken me some time to get them all ready for you guys.
So what would this be labeled as in the notes?
Bode plots. It unfortunately, so the numbering is weird. This is like 21.7 or 8 or something like that, because I just keep adding on to 21. Just so that I don't renumber all the other ones in the middle of the semester on you guys. So I don't know. That's just my.
The link in the Slack were made pretty easy.
Yeah, I did put a
appreciate
link
that.
in there just so that it was clear what was new in there. And I think I might be interpolating a little bit next section as well, because I'm expanding on these topics a little bit. But I think that it's going a little bit slower and expanding on them is going to help you guys a lot in understanding it. My students last year really struggled with this stuff, which is why I'm slowing down more this semester. So I think that was something that when I went back through, I try to have some learning on my part when I teach these classes too. So I learn what's harder and what needs more expansion. So I think this stuff needed more expansion. So this is why we're getting some new lectures that weren't there last year. So
are these on your webpage or are they just in Slack?
they are on the webpage.
What chapter would they be in?
They're under frequency response chapter, which is 14, I think.
So all I'm reading is fundamentals of frequency response and vibration.
Try refreshing the page.
It's down far. I saw it. It says
It's there.
it's called Bode plots.
Oh, that's weird. Okay, it's there now.
Ah, cool. Yeah.
When are we
Sometimes.
planning on having our midterm?
Yes, it's going to be next week. So next week is before spring break. I'm actually open to Monday, Wednesday, or Friday on that because we have, we're going to be covering new material. So I guess pushing it back would allow you guys more time to study and stuff. So I would kind of lean that way, but if there are a bunch of people who are trying to leave early, then we might put it on Wednesday.
Well, I think you guys have a linear test on
I don't know, man.
Friday, right?
I wouldn't mind
Are we
doubling
also
up.
gonna have homework next week too, though?
Yeah.
Then Friday. Yeah.
So Friday.
Yeah.
I do that so that you guys have some practice
Makes sense.
before you take the test. It just seems like it'll help you.
We're still in material, it's in the test, right?
Yeah.
Alright.
Yeah. So we'll finish that up this week.
So it's just gonna be what's covered this week is what we're going through.
Yeah. So we're gonna go through the end of this week for new material, and then so chapter 14 is the last chapter of the textbook and all this material. So then we're gonna start on a new chapter on more stuff to do with this, more frequency response stuff, but different look. So okay, so Bode plots. they're just plots of the frequency response function, okay? Just very specific ones. We've already looked at some plots of the frequency response function, but we didn't plot them in this specific way that we'll learn to. So I say given equation 1.2, equation 1.2 is just our familiar equation. I'll just write it up here. Our familiar equation that, whoa. There we go. That the steady state response to a sinusoid is equal to the input amplitude times the magnitude, maybe. No! I won't even try to make it straight. The magnitude of the frequency response function, that one I got, times sine, do we do sine or cosine? I just forgot. You guys remember? Sine or cosine? Sine. Omega t plus psi, so omega being the input frequency, psi being the input phase, and you can either use phi or this angle notation, angle of j omega, the phase of the frequency response function. So because of this, it's really nice that all we need to know about the steady state solution to a sinusoid is the magnitude and phase of the frequency response function, right? So that's why we're going to spend so much time on those two. Each of these is a function of angular frequency, omega, right? So plotting the magnitude versus omega and the phase versus omega is quite useful. And that's what we're going to do. Bode plots are such plots with axes scaled in a specific manner, and it takes a little bit of discussion to talk about that specific manner, and that's what we'll do now. So a Bode plot is a useful graphical representation of the frequency response of a system. Let the magnitude of u of j omega and the magnitude of y of j omega be the complex amplitudes of the input and the output, respectively, right? So we've dealt with these in the past. So recall that the magnitude of the frequency response function, h of j omega, can be expressed as magnitude of h of j omega is equal to, what is it in terms of this magnitude of y and the magnitude of u? Yeah, magnitude of y over magnitude of u, right? Divided by magnitude of u, j omega. So that was our from our definition, right? Our definition is that h is equal to y over u, and we just took the magnitudes. So, yeah. So this is a ratio of amplitudes, right? It's a ratio of complex amplitudes, well, magnitudes of complex amplitudes. And so it is akin to amplitude ratios commonly expressed in decibels. Okay, we've talked about decibels before. In mechatronics, we talked about them a little bit. dB is the abbreviation for it. However, the magnitude ratio of this equation, we call it equation 1.3, is not dimensionless and therefore cannot be expressed as a decibel in the strict sense. It's a little typo there. As a decibel in the strict sense. So the decibel is dimensionless. It's a dimensionless ratio, right? It's an amplitude over an amplitude. But we can't we can't be guaranteed that the output is going to have the same unit as the input, right? So this amplitude ratio actually is not dimensionless. And therefore, technically, you can't really express this as a decibel. However, that doesn't stop us. We just do it anyways, and it's just become standard in system dynamics and controls to do this. And it's just important. I don't think I'd ever seen this presented in a class before, so I wanted to make sure that we make note of that, because sometimes it like freaks students out. I've seen people get to this point where they're like, wait a minute, what are the units of this? Like, it has units in the equation. Like, if you go back up to this, there has to be a unit, because the output doesn't necessarily have the same unit as the input amplitude, right? You could be having, like, the input could be force, and the output could be, like, a position. And so you have to have a unit conversion happen there. So the magnitude of h of j omega has to have units, right? So we don't want to just gloss over that. We're still gonna use this decibel equation, this formula for decibels, untouched. We're just gonna use it, and we're gonna recognize that the units are just implied. They're implied, but we're just not making them explicit. So it matters if you're expressing your output in different, in different units. So for instance, if you had your output was in meters and your input was in newtons, then this magnitude is going to be in meters per newton, right? This magnitude of frequency response function, meters per newton. And if you decided to do it in millimeters per newton, that's fine, but it would be totally scaled differently, right? So we just have to pay attention to what units we're using in this. It's not a big deal, but it's unlike the other decibels where we don't have to worry about units because they cancel. They don't cancel in this case. We're still going to call it a decibel, but it's not in the strict sense. So nevertheless, it is standard usage of system dynamics and control theory to use the familiar formula to compute the logarithmic magnitude. So that's on the next page. We'll write that down. Do you guys remember what it is? The formula? I don't think that's the formula you remember. So we can write this as like with a subscript dB sometimes, or we can just leave it like this and just put a dB at the end, which is also common. So it's equal to, it's either, so there are two formulas for dB. It's either 10 log base 10 or 20 log base 10. And it depends on if you're taking a power ratio or if you're taking an amplitude ratio. And this is considered to be an amplitude ratio. So we use the 20 log base 10 of magnitude. So strictly speaking, we probably should put dB down there because we're going to use the same symbol over here. And then this ends up being in decibels. So in sort of like air quotes, decibels. Okay, it's weird. Yeah.
What is it? 10 log base 10?
20 log base 10.
No, when is it 10?
Oh, when is it 10? It's when you have a power ratio. So if you wanted to do find decibels and you had the power of each signal and not the amplitude of each signal, if you have the power of each signal, you have to do 10 log base 10 of the power, we call it like power 1 divided by power 0, the reference power. And that ends up being in dB. So that's the other formula.
I think we learned it in intensity.
In intensity?
Yeah.
In physics? Yeah.
But we learned this 10 log time, or 10 log of I over I naught, where I naught is your smallest decibel that can be heard.
Yeah. So when you're talking about
So I think that's why.
sound waves, it's power you're talking about power, so they use the power one. So it does depend. In electrical signals, you can use either the power one or you can use the magnitude one or the amplitude one. So in this one, this is almost arbitrary in the sense that this isn't strictly how a decibel was originally defined. We're just kind of like bastardizing it for this. And I don't really know why we're doing that, but we are. That's just how it is. What it was we needed something that was logarithmic, and it kind of like intuitively is like the decibel. So they were just like, wow, what the hell? We'll just use it. So it works. So this is the magnitude is usually plotted in these sort of air quotes decibels. The phase is usually plotted in degrees. And the omega axis is logarithmic in both plots. Okay, so it's magnitude versus omega frequency, and phase versus frequency, and the omega is also logarithmic. Okay, so you guys have seen some logarithmic plots before, which is good. They're a little weird at first, but they're really convenient for showing certain things, and they're convenient in this case. Because they end up being sort of straight line, asymptotic to straight lines, so we can sketch them by hand, whereas if we put it on a linear scale, it would not look anything like that. It would be like a curvy thing. It's not easy to do. Also, you can add them together on a log plot. We'll get there. So the two plots, magnitude and phase, are typically tiled vertically with a magnitude plot above the phase. So magnitude, phase. And we do them vertically for a specific reason. It's because both of them are plotted versus omega, right? Versus frequency. And so to the right from the origin is the same frequencies matching up in the plots. So you can see where the magnitude and phase is at each location in each frequency. You can see where the magnitude and the phase is by just drawing a vertical line from one graph to the other. So it's convenient that way. You could actually plot them, it's just not standard to do so. You could plot them on the same graph and have two y-axes, right? Two vertical axes, but that's not standard to do. So, okay. So a simple Bode plot. So let a system have the transfer function just s, so just a single zero at the origin. Find the frequency response function and draw the Bode plot for the system. So we're going to do a work here on this page, and then on the next page we have a nice logarithmic scale for us to draw it on. So let's do this. So, from the definition of frequency response function, well, actually, it was the formula right after the definition. It told us that h of j omega is equal to the transfer function, h of s, evaluated at s equals j omega, right? And that is just equal to, we just plug in j omega in there. It's equal to j omega, because our transfer function is just s. So that was easy. We got the frequency response function. Pretty easy to do. Now, this lies, so we're thinking about this in terms of the complex plane. This lies on the imaginary axis. It's all imaginary, right? with magnitude. So we could plug this into the magnitude of the frequency response function formula that we wrote down, which is that it's the square root of the sum of the squares of the real and imaginary parts. Just using Pythagorean theorem in the complex plane to decide how long it is. Sort of like a vector in 2D, just finding the length of it by Pythagorean theorem. We could do that, or we could just say, oh, hey, it's all just in the j direction, right? It's all imaginary, and so its entire length is just going to be omega, right? Has to be. I mean, we could do the whole square root of the sum of the squares, and we're going to find out that, oh, wow, it's just omega. Do you get that? If we let's draw a little sketch over here for ourselves. If we have on the vertical axis the imaginary and the horizontal axis the real, so real and imaginary. And we draw this is omega, that's the imaginary part, right? It's all imaginary, no real. So its length is going to be omega. Okay? My calendar wants me. It's like, boom. You guys, it was so ridiculous this morning. I never leave my laptop anywhere. I bring it with me like everywhere in life. It's too much, really. But I bring it with me everywhere, and I somehow left the house this morning and just forgot it. I don't know that that's happened in like 2 years of living in this house and driving in here. Hasn't happened. Okay, so I get to school and I look over in my bag and I'm like, that's light. That's light. It does not have my laptop in it, and sure enough, it didn't. So I just turned around and went back. Did not check my phone, however. I get back. Niles greets me, so happy to see me, yeah. And then I go looking for my laptop, and that's not there. I'm like, okay, where is Ashley, my wife? I'm like, go look for her. She's not there either. I'm like, uh-oh. So I look at my phone, and I've got like 50 calls, not 50, but a lot of calls and a lot of texts, and it's like, she's like, I'm in the parking lot. I brought you your laptop. And I was like, no! So then I had to wait for her to come back because I didn't want to just like leave my laptop somewhere here for me to come get it. So like I waited for her to come back. So needless to say, I was late for office hours this morning. And I just felt like telling that story. My day has gone like that so far. It took me like an hour to get to work with my laptop. So
Your wife is so nice, though.
Right.
she really was. I was like, that was so nice of you to do that. It didn't even occur to me that she would notice. And then she just like came. She like sent me messages. She's like this whole thing like, oh, you forgot your laptop. And then like 6 minutes later, I'm on my way with your laptop. And then like, I'm here at the parking lot. And like reading these in my living room. I'm like, oh no, that's not good. So, anyways, thanks, babe. So this is just omega, right? Assuming omega is positive. We are going to assume in all of our frequency response function analysis in chapter 14 that omega is positive. But in chapter 15, we will start talking about negative frequency. It's cool. It's actually, it just like mirrors the positive frequency. So.
Now I got my question.
Yeah, what's your question?
Took a minute to formulate something.
I was stalling for you.
Thank you. So if you have more than one zero, so you find your whatever numerator makes zero, and you have a bunch of them, and like you need to like factor it so that it's like j times something to get your like absolute that you're trying to get, like times j, like can your absolute be more than just a w? Could it be like another quadratic equation or like something to that effect?
Oh, for sure, yeah. Yeah, so so omega, it could be some complicated function of omega. It is going to be real, however, because
it has to be like in some
magnitude.
form of omega. But it would be
Yeah,
like-
some function of omega.
okay.
I mean, unless it's a constant, it can also be a constant. Otherwise, it's a function of omega. You can have, so here's the thing. So right now we're going to go through and actually find the frequency response function, find the magnitude, find the log, etc. Then we're going to learn how to plot these things, sketch them, without finding the frequency response function, going straight from the transfer function, which is pretty sweet. So we don't actually have to expand all the complex stuff to do the Bode plots, which is good news because expanding them is really a pain.
I was gonna say something like the equations to find the zeros are not simple.
Yeah, so if you had like a fourth order system in the denominator, you've got a whole lot of stuff to mash together. In the numerator, you've got a whole lot of stuff to mash together if it's got some zeros in it. So yeah, it's a mess. I mean, it's not that bad, really. It's at the end of the day, it's just going to be a complex number over a complex number, and then you got to rationalize it. So it's not really that bad, but it can get messy to write down.
Algebra was.
Yeah, I mean, conceptually, it's the same as a simple problem, but let's write it in dB. So we're going to plot it in dB. So that's going to be equal to maybe 20 log base 10 of omega, and we'll just put dB out here. Okay. Now, that's the magnitude, and it's going to have a phase as well. The phase, we have a formula for that. Do you guys remember what it is? It's the arctangent of something over something. It's the imaginary over the real, right? Imaginary of h of j omega divided by the real of h of j omega. So this is, if we could plug that in and take the arctangent, or we could just look and see, oh, what is this angle going to be? 90 degrees. That's right. But you could always go back to the arctangent, 90 degrees. So let's plot. So the Bode plot is shown below. Actually, we're going to draw it. So (20 log 10 of omega) we need to draw on this axis here. So one thing we could do is just like do a couple points if we're unclear, right, on like where it should be. So first thing is let's evaluate it at 10 to the 0, which is what? 1. So what is log base 10 of 1? Do you remember?
10?
No, but I mean like you're thinking along the right lines. Something very distinctive. 0. 0. So we've got a point there. So 0 dB. So 0 times 20 is going to be 0. And then what is 20 log base 10 of 10? 10 to the 1 is 10. So log base 10 of 10 is 1, so times 20. So we've got 10 and then 20 dB. And then what is log base 10 of 100?
Are you going on a limb to say the answer's gonna be 40?
Yeah, well, it's 10 times 20, or sorry, it's 2 times 20. It's 2 times 20 is 40. And as you can imagine, if you do this down here, you'll continue to get points along this line, right? See how well I did with my point drawing. Not terrible.
That's not bad. That R value is pretty small.
Yeah, it's pretty. Yeah, you're right. I'd call it like pretty solid. Pretty solid.
Like maybe the
I do have a little bit of a bias towards low, though.
yeah.
So, of course, maybe my line is biased high. So there's that. So then, what about the phase? The phase is not, we don't have to worry about any of this. So so first of all, omega, yes, is logarithmic, but there were no issues with that. But it is nice. It is nice to recognize. This goes down to 0.001, 0.01, I should say, and it goes up to 100, and that all fits on this scale here. And what this logarithmic frequency does is it actually sort of stretches out what happens at low frequency so you can see it better, and it sort of smushes in what happens at high frequency. It's kind of the effect of it. So sometimes logarithmic is helpful. The phase, we calculated it to be 90 degrees, right? Which does not depend on omega at all. So that's pretty easy to draw. It's just 90 degrees across. So we have constructed our Bode plot. Brute force wise, we didn't actually use the elegant way that we will learn, but we did it brute force. Okay.
Like, you know, there's always gonna be one phase change, right? So like, is that not true?
So the phase can also be a function of omega.
Oh, it just wasn't here because the point was just happened to be. So if this is a real end measuring part, it's gonna be on an angle. Get all crazy here.
Yeah. Well, yeah. So we'll see. So essentially, the imaginary and real parts of h of j omega are functions of omega typically, and they end up being there are transitions in phase. So we'll talk about the different types of phase plots, and actually that's the next thing we'll do is go through a bunch of different types of Bode plots for different types of systems. But first I have this discussion that's going to hopefully motivate it, and it's going to help us understand a little bit more how these Bode plots are constructed and why they're constructed in this way. So far I just said this is what Bode plots are. Here's how to make a Bode plot brute force wise. But now we're going to learn a little bit more in detail about Bode plots, and maybe they'll become a little bit more clear to us, and we'll be able to construct them and use them a little bit better. So it turns out that when plotted on this logarithmic scale, recall that the omega axes are plotted logarithmically as well, not just the magnitude. Both the magnitude and phase are quite asymptotic to straight lines for first and second order systems, and for constants. So for simple systems, these systems are asymptotic to straight lines. Furthermore, higher order system transfer functions can be rewritten as the product of those of the first and second order systems. For instance, so if you have this transfer function, and I just put in these blanks here for coefficients, then put coefficients in. So it's got how many zeros? 1, 0. And how many poles?
4. 2.
Average. 3.
Oh.
It's 3 because there are 3 values of s that will satisfy cubic equations. Quadratic, it would be 2. Yeah. So there are there's 1, 0, and 3 poles. Now, what I just told you is that we can rewrite this higher order. It's a third order transfer function, right? The system order here is third because we have an s to the 3, which is going to be, so if it's a second order system, it's going to be the highest order, and the denominator is going to be s to the 2. If it's a third order system, it's going to be s to the 3. So it's a third order system. We can rewrite it as the product of this second order system, perhaps. I mean, this is one possibility. A second order system, another second order system, and the denominator, you factored this out essentially. And then the numerator, we can separate it out to be its own thing, so it doesn't have to be on top of one of these, and then a constant. So you can always do that with your transfer function. You can always break it down into first and second order components. You can actually factor this out and have all first order if they all end up to being real. If you can actually factor this with real numbers. If you can't factor it with real numbers, you should leave it as quadratic. Okay. All right. So you can always break it down into first and second order system so that it multiply together. Then, so we've got these pieces. We're sort of linking up in this chain. Okay. So first off, for first and second order systems, we're asymptotic straight lines. So that's nice. For higher order systems, we can write the transfer functions as products of first and second order systems. So that's also nice. But I don't know about you guys, but taking products of lines is not like the easiest thing to do graphically. And this is actually why, this is the big motivation for why we're doing this logarithmic thing. Okay, this is the big, I mean, it's nice that it's straight lines, yes, but also one of the big reasons is that we can use this nice fact. So first off, the phases, if you have in this sort of phasor notation, if you have complex numbers that are combining together, are multiplying, the magnitudes multiply and the phases add, right? We've known that for a while. So, and this is just an example. So if you have one complex number, m1, so has a magnitude, has a phase. This one has a magnitude and a phase, but it's in the denominator, and so does this 3. The magnitudes multiply and divide each other. So m1 divided by m2 divided by m3. And the phases just add together. So if it's in the numerator, it's positive. If it's in the denominator, it's negative. They just sum. So this is true. This has been true for like phasors and everything like that. But also just whenever you do complex numbers, if you want to combine them using magnitude and phases, this is true. Now, so the phases are nice because graphically adding things is really easy, right? You add two things together. Like you guys have added graphically for a long time. Probably some of your earliest exercises with graphs was like adding two graphs together, that type of thing. So it's not too hard to add graphically. But this magnitude thing, it's multiplied. They're multiplied together. And multiplying graphically is not easy. And dividing graphically, it's not easy. So if you take the logarithm of the magnitudes, they add, right? So that's one of the log properties. If you take the log, any log, with any base, they sum. Each log, if you expand it out, sums with the other log. So if we were to plot the magnitudes logarithmically individually, then they would also sum. which is nice, which is the whole reason why we're doing this logarithmically, or at least that's the main motivation for doing it logarithmically. So you can add them. There's only one more link in the chain. Okay, first and second order Bode plots depend on a handful of parameters that can be found directly from the transfer function. So we can draw these sort of straight line asymptotic approximations just by knowing things like what's the time constant of a first order system? What's the natural frequency of a second order system? And we're going to call these special frequencies the break frequencies, okay? And it'll allow us to do sketches of these. And people, you know, might take the perspective that why even do hand sketching of Bode plots now? I mean, you can just plop it into MATLAB and it'll just, bam, it'll plot it for you beautifully. And it's because we want to be able to understand these systems at a level deep enough to know how our design decisions are going to affect it. If we know how to construct, if we have a sort of internal model for how to construct the Bode plot, then we're going to have an internal model for how to change the Bode plot to be how we want it to be. And that's really why we're doing it. People used to do this because they wanted to know what the Bode plot looked like at first, and then they wanted to change it. But now we do it just as a design tool to have an intuition for if we were to change the time constant by this, how would that change the Bode plot? We do that so that we have a feel for how that would change the Bode plot. Okay? So that's kind of the big... It kind of feels like we're learning this archaic thing, like how to sketch things, but it's actually a way of honing our intuition for designing these systems. And that's really the value in it now. Otherwise, I'm a huge fan of throwing away archaic things. I really like doing that, but there's value in some of them, and we have to pay attention to. And this one, I think there's value in it. Just like, there's value in a lot of sort of by hand graphical things that we don't use in the same way that we used to use them, but this is one of them. And controls, there's quite a bit of this stuff. Do you guys remember Moore's circle? Yeah. Moore's circle is another example of that. It's, you know, you could just, the formulas, you could just have them in you know, programmed in and just find out what the max stress is and all of that. But getting a feel for the different dimensions of stress is really helpful.
Yeah, because 1 and 2, sigma 1 and 2 are the eigenvalues of your thing, right?
Yeah. You guys talked about eigenvalues with stress?
No, I
3 seconds of machine design.
Oh, that's cool. Yeah, that is. I wish you guys could. This is something that I've often bemoaned in engineering education, is that a lot of times we show you guys stuff before you know the math to really get a deeper level of it. And that's just because we have to cram so much in, and there's no way to get you guys, we can't really require that you go through all of math before you start any engineering. But for machine design and for mechanics of materials is really where that comes from. And that's, you learned it the first time without any of the linear algebra aspects of it. And then when you come back the second time, usually they don't talk about it too much again because you aren't familiar with it. So anyways, it's my own little thing. I'm always thinking about how to make the curriculum better. But all right, so the last link, okay, is that we have this handful of parameters that can be found directly from the transfer functions to construct these simple ones. And then once we have the simple ones, now this chain is complete. If we have the ability to construct these simple first order, second order, constant transfer functions, from the those plots from the transfer functions, they're going to combine by just adding with each other, right? Because we can rewrite them as products of these simple systems. And like we said, the phases are just going to add, so that'll just be graphically added. And since we're doing a logarithmic plot, The magnitudes are just going to add. So we'll just have to do them each individually, and then we could sketch out a fifth order system with 3 zeros in it, no problem. We would just have to do them each individually, and then we graphically add them. So we'll learn how to do that. Probably, I don't know if we'll get to it on Wednesday, but on Friday we're going to get to it in detail. We're going to go back to that vibration example, and we're going to do the Bode plot example.
So we're gonna find like these magnitudes and phase changes and stuff, and see how like the numbers correlate to finding these things. And I'm looking at it, like I understand what they are. So I'm trying to associate with what I pull the M and the phase change from.
Yeah. So, you mean like, what are they as far like how can you get a feel for what the magnitude and the phase are, or like intuitively, or what is it? Sort of, what was your question?
I'll have to think about that and
Yeah.
reform it for next time.
Well, fortunately, we're gonna be talking about this in the next couple classes, so we'll try to reformulate it by the next class. Well, looking forward, all we're going to do is go through and look at the frequency response function, the Bode plot for these simple systems. And just to give you a little preview of that, this is the one we did in the example problem, right? This stack. This stack is what you have if you have one pole. This is what you get if you have 1, 0. This is for a real pole and a real 0. So this is a real pole, a real 0, and then there's the second order complex conjugate pole pairs. And these ones are definitely the hardest, but notice this little thing that's happening here. That is the resonance peak, okay? It's a resonance, second order system. So anyways, we're going to talk a little bit about that, and then we're going to talk about sketching the Bode plots by hand. So look forward to that on Wednesday.